So our third and final method of standardization, at least in this class, makes use of these things called internal standards. So I get it, the names can get a little confusing, external, internal, standard edition, etc. But with practice, you'll sort of get the grasp here. Internal standards can be used as their own standalone standardization system for instrument response, but often they're not. They're used in addition to either external standard calibration or standard edition calibration. And they are used in addition to ensure that we don't have instrument drift or matrix effects contributions to our analysis. So they're like a bonus check for our calibration. They can be used standalone. Some people do that, but it's not the best practice. So internal standards are similar to standard edition, but slightly different. They're similar in that you're going to add something to your samples, but you're not adding more of the analyte, which is the case for standard edition. You're actually going to add a wholly different molecule or compound or ion, depending on what you're trying to analyze, and you want that thing that you're adding to be known, something you know, but you want it to be different from the analyte and selectively different from the analyte, something that your instrument's going to respond to differently. But you want it to respond to differently, meaning you can differentiate it, but you want it to behave pretty chemically and physically similarly in terms of the response that it's going to generate from your instrument or your method. The idea is that if you add to your sample, so in the case we're just continuing with this sort of same example, you've got this sample, water sample, it's got some lead in it, that's what you're trying to analyze for. For your internal standard, you're going to want to choose something that's like lead but not lead. So that would probably be something that is an ion, a metal ion, heavy metal ion, that's similar in its behavior in the instrument that you are using. So for atomic absorption, that means you probably want something that's similar in mass. So you look at the periodic table, you say, well, it's next to thallium, maybe we use thallium. You also want to consider how well it ionizes in a flame because that's the type of technique you're using, and it turns out thallium's pretty similar, super toxic, but you're only going to use a little bit. So that means you can add thallium to all of your samples and your standards. So everything is going to get thallium, but it's going to get thallium at exactly the same concentration in everything. So you're not creating this iterative calibration curve. Now instead, you're just adding a control to every single thing that runs through your instrument. And you know the control one, and you know the concentration is the same in everything, and that thing that you're adding, in this case thallium ion, is going to be essentially a proxy for the behavior of lead. The reason you do it that way is because now, if you've got your instrument, right, and say you are analyzing, this is your instrument, this is your atomic absorption spectrometer, and you shoot some of your sample in there, right, and let's say you've got 1,000 samples to run, but every single one of them has this internal standard in it. Over the day, if your instrument starts to drift and the response starts to change, over the duration of the day, you know what the response of your thallium, TL, ion should be, right? It should be the same because you have it in every single sample. At the same time, if the matrix is different across your samples, which is hard to compensate for, then knowing that thallium is in every single one of your samples, you should get exactly the same response for thallium in all of those samples. So in other words, if you have, say, let's just draw this up. Say you're calibrating your instrument using external standardization. So that means you've got these 5 standards that I have highlighted here. So you've got 5 standards, external calibration. You've got 4 samples that are in these flasks here. You want to run all of these things, and what you do is you add the same amount of thallium to every single one of these things, all of them. It's standards, the external standards, and the samples. So every single one of them gets dosed with the same amount of thallium, some small amount of it. Then when you look at thallium in your instrument response, we'll say you have thallium, we'll just say response on this axis, and then we'll say sample number down here. So we're talking about sample 1, 2, 3, 4 and standards all the way up. So all of these, right? There's 9 of them. What you would hypothetically expect for thallium, so I'll do that in blue, is that the thallium doesn't change, right? Every single time the response is the same because you have the same amount in everything. But if the matrix is different or the instrument starts to drift, then you start to see maybe deviations in that thallium signal in the response, even though it should be the same, right? It should be the same because you added the same, should be the same, the internal standard. So the punchline here is that if you're monitoring in every single thing you run, if you're monitoring a control, you know it should be the same, then you can actually compensate if it's not the same. So if you have your analyte and you're measuring that response too, this is lead 2+, and we'll do this in green, what you would assume then is that the response for that lead would also track this, right? So if the thallium was unchanged, the lead, if you chose the right internal standard that was chemically and physically responsive similar to your analyte, it should also then behave similarly if the instrument drifts or if the matrix changes. Those intensities should track pretty well, and you start to see the same sort of response changes. So as long as you're monitoring that, so imagine for a second if you didn't have thallium there and all you saw was lead changing across these samples and standards, how would you know that that wasn't simply due to different amounts of lead in those things? You wouldn't. You'd have nothing to tell you that. So what you essentially have is sort of this insider information that tells you that it should be the same, but it's not. It's changing over time. So if lead is changing over time, what we can do is sort of do a ratiometric compensation for this, where we would take then the lead signal divided by the thallium signal as a function of the sample number here. And what would happen if we took the ratio of the blue to the green intensity here? Well, if they're tracking the same every time, then what we have is a new adjusted response where everything is normalized, nothing is changing. So we're compensating for the change in lead that's due to matrix or drift effects by adding exactly the same amount of a control substance to each one of these. As that changes, we can use that as sort of the common denominator. We divide that into the signal that we get for our analyte, and that normalizes the intensity for those oscillations over time. That's the purpose of an internal standard. You can use an internal standard either in external standardization or in standard addition. Either one, the same thing is true here. And so what we would get is an intensity or a response that's been adjusted. That new adjusted response, whatever that is, then gets fed into whatever the generated equation of the response line is. So you would take that response, plug it into y equals mx plus b, and now you would have a compensated concentration value when you calculate x that's been adjusted for any effects based on changes in the internal standard response.